In previous videos we have talked about how to compute the channel capacity exactly when we have Gaussian noise and when we know the channel perfectly at the receiver side. But what if we don't have Gaussian noise? We might have something that is non-Gaussian, maybe containing interference or disturbances, or if we don't know the channel perfectly. Well, in those cases we can't compute capacity exactly, but we can compute capacity lower bounds, which are representing achievable rates, bit per symbol, that we actually can transmit at. In this video I will go through the technical assumptions behind several different bounds, and I will present you with the proof techniques and talk about how we can utilize these particular bounds. We will begin by considering a case that is familiar from previous videos, the capacity of a complex discrete memoryless channel, where we are transmitting a complex signal X. It has a certain power Q. It's going over a channel G. All variables here are scalars. We are adding independent complex Gaussian noise N with N0 as its variance, and what we are receiving is Y, which is G times X plus N. And it's a memoryless channel because we are transmitting one signal X and we are getting one signal Y and one independent noise realization. And next time we transmit, we get a different X, a different N, and a different Y, while the channel G here is constant. The channel capacity is a measure of how much information we can put into X and still be able to extract it in Y here due to the noise and the scaling here. And the channel capacity can be written in this form. We are maximizing over the random distribution of the signal X, and we can take the differential entropy of the received signal Y, so this is the uncertainty or surprisal in Y, minus the differential entropy of Y given X. And this term is representing the randomness imposed by the channel, namely N here. We can also write this expression in the opposite order. We can take the differential entropy of the input signal X minus the differential entropy of X when we know Y, and we can maximize the difference with respect to the input distribution. On this slide I will use the first of these two options, and later we will use the second one, and the choice really depends on what kind of proof technique that we are utilizing in order to compute the capacity. One thing that will be important as well is that these differential entropies are lower bounded by log 2 of pi e, and then if it's the variable y that we are computing the differential entropy of, then it's the variance of that variable. And equality is achieved when y is complex Gaussian distributed. So among all random distributions that are having a particular variance, the complex Gaussian distribution is the most random one in the sense of information content. So that is why we often like to utilize that distribution in order to maximize the information that we can transmit. So to recap how we are computing the capacity in this particular case, if we start with the upper line here, we have the differential entropy of Y given X. If we know X, we can subtract G times X from Y, which is then meaning that we only get the noise N left. And we know that the noise is complex Gaussian distributed and it has the variance N0. So therefore from this expression here we replace the variance with that variance, and this is the expression that we're getting. And everything here is just equalities. So we're just computing it. There is no bounds, or we are still treating any input distribution. When it comes to the first term here, the differential entropy of Y, we know that for a given variance of Y, so we can compute the variance of this term here. We know that among all the distributions that could have generated that one, we would like Y to be complex Gaussian distributed, because then we get the largest possible value. And that happens precisely when X is complex Gaussian distributed with the variance Q that we would like to put into it. In that case, Y, which is equal to G times X plus N, is also complex Gaussian. It has this variance where we are summing up the variance of the first term and the second term. We put into this expression, utilizing that we have the maximum entropy kind of distribution, and here is the variance that we are getting. So here we have figured out what distribution we should utilize in order to maximize this difference, namely the complex Gaussian distribution. So the channel capacity is now the difference between this expression and that expression, We put in the two different expressions. We utilize that when we have the difference between two logarithms, we can also write as the logarithm of the ratios of the two terms. So we take this term divided by this term, the pi e cancel out, and we get 1 n naught divided by n naught. It's the 1 here, and we get q absolute value square of g divided by n naught. It's this term that we call the signal to noise ratio. So this is the capacity expression for a complex discrete memoryless channel, and the underlying assumptions here is that the noise is complex Gaussian, it's independent of the input signal x, and we know the channel g at the receiver side. Then we get this expression that should be familiar to you. But what if the noise is not Gaussian distributed, and it's not necessarily independent, say that it's only uncorrelated? So we consider the same setup as before, but now the only thing we know about n is that it has zero mean, it has a variance that we call n naught, and it's uncorrelated with the input signal x. So if we take x conjugate times n, compute its expected value, it's equal to 0. Apart from this, it can have any distribution, and there could be a statistical dependency between x and n, even if they are uncorrelated. We cannot compute the capacity exactly for this type of setup, but we can compute the capacity lower bound, something that is achievable, something that is below the true capacity, and therefore we know that we can encode information to transmit in that particular way. And in preparation for that, let us first go through a number of things. Suppose that we are receiving y, and we would like to compute an estimate at the receiver side of x. We are not caring particularly about the capacity right now, but just estimation theory. So in addition, say that for a given y, we would like to compute a linear estimate of x. So our estimate x hat should be a constant that we will find multiplied with y. What would be a good value of this constant? Well, we know that there is something called the mean squared error, where we are taking the true value, subtract the estimate, we compute the absolute value square, and we compute the mean value of that. That is the mean squared error. And in this case, if we are subtracting x hat, which was c times y, and we are computing this term, you will see that there are some terms that contains x. It's this x, and it's the x that comes from c times g times x. And if we are expanding the expression, we are getting 1 minus c times g, we get an absolute value square, and we get q, which is the power of x. Then there will be a noise term, n multiplied with c, which is showing up here. And if we are computing the expectation with respect to that one, with absolute value square, we get absolute value square of c, the constant, multiplied with n naught, which is the variance that we know about here. Finally, when computing something like this, there are two sources of randomness. There is x and n inside of it, and there will be several cross terms containing x conjugate times n and n conjugate times x, and these terms will be equal to 0 due to this assumption of them being uncorrelated. So that's why we only have these two different terms. If we want to find the c that makes this mean squared error as small as possible, we can take derivatives or utilize completion of squares or various methods in order to find that the c that makes this as small as possible is this particular term. I will not go into more detail on that right now because the focus is not on that minimization, but what happens to the mean squared error. So if we take this value of c and we put it back into the mean squared error expression, we can compute the minimum mean squared error for this particular type of estimators. And this is the expression that we will get. And actually what we have obtained here is also known as the linear minimum mean squared error estimator. And this is only the best choice of estimator among the linear estimators that can be written in this particular form, but among all conceivable estimators, including those that are non-linear, we know that the mean squared error that we could achieve will be small or equal to the number that we have computed here. So we could have utilized any technique, any estimator here, but this is at least an optimized one obtained in this particular way. What we should remember from this slide is that if we are obtaining y at the receiver side and we compute some kind of estimator x hat of the transmitted signal x, then the mean squared error will be small or equal to this particular term. Now we will utilize this to compute the lower bound on the capacity of this particular channel where we have arbitrary uncorrelated noise. And remember, we had two ways of writing up the capacity definition. Now we utilize the second one, where the capacity is a maximization with respect to the input distribution, the randomness of x, and the variance is set to q, but all other things that has to do with the random distribution is things that we can select when we are maximizing with respect to the PDF. Then we should take the differential entropy of x minus the differential entropy of x given y. And we will compute the lower bound in two steps. When we are computing lower bounds on the capacity, we are free to make assumptions, things that we are not sure about if there are optimal ways of operating or not, but as long as we can operate in that particular way, we will obtain a lower bound on the capacity. Our first assumption is that x is complex Gaussian distributed with q as its variance. So this is what we know was the optimal way of transmitting when we have Gaussian noise, but now we don't know if that is going to be the case or not. But as a potentially suboptimal way of designing our transmitted signal, we can make this assumption. It might not maximize this expression, but it will give us one value of it. In particular, we will get this value. So the capacity is greater or equal to what we get with this particular input distribution. And now the differential entropy of x is given by the expression we had before because it's Gaussian distributed. Log 2 of pi times e times the variance, which is q in our case. Now we still have the second term, differential entropy of x given y. We will now bound this conditional entropy, and in particular look for something that is a larger value than the true one, because then we are subtracting something that is larger, and we continue to get a lower bound on the channel capacity. So here is the conditional entropy. And remember, we had computed this linear MMSE estimate of x given y on the previous slide. And this was just to take y and multiply with the constant c. So we can replace y with this new x hat, and there will be no loss of information because there is only a constant c in between. So if we know x hat, we can always divide by c and go back to y again. Now, say that we take x and we subtract x hat from it. If we know x hat, that doesn't change anything about the uncertainty about x, because we still know x hat. We can still add it again and get back the same result. However, if we, after we have subtracted x hat from x, throw away x hat, we no longer know that information, then we get this differential entropy of x minus x hat. And we should get something that is larger because we threw away information and therefore we have a larger uncertainty. And there is no guarantee that x minus x hat will be Gaussian distributed, but it is representing the estimation error. And then we know that if the estimation error would be Gaussian distributed, then the differential entropy can be computed here as log 2 of pi times e times this expression, which is representing the variance of this term. It's also the mean squared error from the previous slide. And if it's not Gaussian, we get something that's larger, and if it's Gaussian, well, then we have equality in this part here. And then from the previous slide, we had an expression for this term. It was this expression. So now we have one lower bound up here, where we were assuming that we had Gaussian transmission signals. And then we have an upper bound on the second term, which is additionally adding to getting a lower bound on these things. So our capacitor lower bound is this term minus this upper bound on the second term. So we get this term minus that term. And since we have a difference between two logarithms, we take this term, we are dividing with the second argument, and then we see that the pi and e terms are cancelling out. We see that this q is cancelling out that q, and then we should take this expression and turn it upside down. The n0 and n0 are cancelling out, becomes a 1. We get q, absolute value square of g, divided by n0, and this is the term that we're getting. So now we have a capacitor lower bound that is applicable when we have arbitrary noise added to our received signal that has zero mean, has a given variance, but it's only assumed to be uncorrelated and can have any distribution. You might recognize this expression because when we had independent Gaussian noise, we saw that the capacity exactly was log 2 of 1 plus this SNR term. And now we have seen that when we, instead of having independent Gaussian noise, have arbitrary noise that is uncorrelated but have the same variance, well, then we know that the capacity is greater or equal to log 2 of 1 plus the same SNR. So that tells us that the capacity with uncorrelated noise is potentially larger than the capacity that we are getting with independent Gaussian noise. So we can say that the worst case type of uncorrelated noise is the independent and Gaussian distributed noise, because in that case we know that we have equality, and otherwise we have a capacity that is greater or equal to the same term. And in any case we achieve the bound by choosing to operate with Gaussian signaling. With independent Gaussian noise, this is the capacity achieving way of transmitting, while it's probably not the optimal way of transmitting when we have arbitrary uncorrelated noise. But if we choose to transmit in this way anyway, well, then we can achieve this lower bound. Why is this second type of expression interesting? Isn't noise something that is independent and Gaussian distributed? Yes, that might very well be the case. But it is giving rise to a principle called treating interference as noise. Namely that suppose n is not only containing Gaussian noise that is created in the receiver hardware and is well modeled as independent Gaussian, but it also contains other types of noise-like signals. Something that might be non-Gaussian. It can, for example, be some interference terms or some disturbances from other types of systems. And then we know that as long as we are computing the variance of n, we can put it here and we can get a lower bound on the capacity. And importantly, this is a bound, it's not an approximation. There is no approximation involved here. We're just choosing to maybe suboptimally transmit using Gaussian signals, but we can make that choice, and the receiver is choosing to decode the signals in a particular way by treating the interference as being noise, treating what we are receiving in addition to our signal as being something that is uncorrelated and in the worst case is Gaussian. So let's design our receiver algorithm so with the worst kind of noise, namely the Gaussian one, it is working flawlessly, and then if we have another structure there about the noise and interference that we don't know about, we can still treat it as being the worst case scenario, namely that also the interference is Gaussian distributed. And if we know something more about the structure, we could potentially achieve something that is close to the capacity than this lower bound, but we at least know how to achieve it. And remembering the proof that we were going through in order to obtain this bound, what did the receiver do? It was trying to estimate the transmitted signal from the received signal using a linear MMSE estimator. And if the transmitted signal is Gaussian distributed and the noise is Gaussian, well then we know that the linear MMSE estimator is the same thing as the MMSE estimator and therefore it's optimal. Moving on, we will now consider another complication that can appear when we are computing capacities. Namely that we have a fast fading channel, a channel where G takes a new realization every time we transmit a signal X. And then we still have some kind of uncorrelated noise term that we're adding here when we are receiving Y. And if G is varying that quickly, there is really no way for the receiver to obtain the realization of G. So we need to build a way for us to estimate the data that was transmitted to obtain a channel capacity without knowledge about the channel G. We make one assumption, namely that the transmitter doesn't know G either, so X is going to be independent of G. Some further technical conditions are required. In particular, we will assume that n is uncorrelated noise, which is now both meaning that x tilde times n, if we compute the expected value, it becomes 0, just as in the previous example. But now, since we have a random channel g as well, we also multiply with that one because we have the term g times x here. So if we take the conjugate of that term, multiply with n, compute the expected value, it should be 0. Then we have uncorrelated noise, both with respect to x and g times x. The problem for the receiver now is that it neither knows G, nor X, nor N. So how can it extract any type of information for this? Well, we can rewrite the received signal like this. We are adding a term, expected value of G times X, and then we subtract the term again. So we take G that we already had, we subtract minus the expected value of G, multiply with X, and then we had a noise here still. And expected values, these are deterministic numbers, constants. So of course the receiver can know such things. So now we have one term here where we know this constant. We don't know the data signal, but we can treat that as our effective channel. the expected value of G. And then everything else, we will treat it as some kind of effective noise term. So even if it contains some of our data, we have no idea about what G minus its mean value is going to be, because this is a random number. So let's treat it as being part of the noise. And now we have something that is resembling the case that we had treated before, a constant channel times the data signal plus noise. But if we should utilize the capacitor lower bound from before, we need this effective noise to be uncorrelated with x. Is that the case? Well, then we need to take x conjugate and multiply it with this term and see if it becomes 0. And then we have x conjugate multiplied with x, and we have an absolute value square of that. And we have x and g that are independent of each other, so that's why I've separated these two things. I compute the expected value of this term, expected value of G minus expected value of G. So I have a term like that here. And this is of course equal to Q, but expected value of G minus itself is of course 0. So this term is 0. The second term is x conjugate times n, this term, and that one was assumed to be 0. So yes, we have an effective noise that is uncorrelated with this term. And now it becomes very important with this notion of uncorrelated noise, because of course x is appearing within the effective noise term, yet it is uncorrelated, this data signal and this effective noise term. So that's why we can apply the same capacitor lower bound as before. Now our effective channel is expected value of G, so we have a capacitor lower bound which is log 2 of 1 plus the power Q that we're transmitted with, the effective channel with an absolute value square, and then we should take the variance of these two terms. We can either put it down here, divide with it, or by utilizing the second condition here, we know that when we are computing the variance of these two terms, they are actually not affecting each other, uncorrelated with each other. So for that reason, we can take the variance of this term, which is going to be Q from the power of x. The variance of G is showing up when we are computing the variance of this term. And then we are getting the variance of noise. So this is the capacity lower bound that we can utilize when we don't know the channel. Let us take a closer look at this capacity lower bound. Here I have repeated it. In the signal term here, we have the expected value of the channel G. And when we have a random channel, actually, most random channels have an expected value equal to 0. If that is the case, we put in the 0 here, and we have 1 plus 0 in the entire expression, which is 0. So then we have a capacitor lower bound that says that the capacity is greater than 0, which isn't very informative. It doesn't say that we can transmit any data. So in general, this is a very lousy capacitor lower bound. But even if G have a mean value which is equal to 0, its absolute value typically have a mean value that is non-zero. So the thing is that the absolute value of the channel is varying between 0 and upwards, and then G have a complex phase that is rotating and is equally distributed over all the angles. So that is what is creating this 0 mean, while the absolute value doesn't have 0 mean. This property can be utilized, and it's the core of something called the use and then forget technique. And I will explain you in a moment why it's called like that. So suppose we are receiving a signal which is behaving similar to what we said before, but now I will call the received signal y prime, the channel g prime, the data signal is still x, and the noise is n prime. Now suppose we know g prime at the receiver side. Then we can utilize it to pre-process the received signal before we try to decode the data. So we do it like this. We create a new signal y by taking y prime and multiply it with g prime conjugate, and then I normalize with the magnitude of g prime. Y prime have this expression, so if I replace y prime with g prime x, I get the g prime conjugate times g prime divided with the absolute value of g prime. That becomes the absolute value or magnitude of g prime. And then I multiply this with x. And then I get this expression multiplied with n prime, like this. And if I now treat this absolute value of g prime as my channel g, then if g prime have an absolute value which have an expected value that is non-zero, well then I can utilize this type of bound and get something that is meaningful, something that have a non-zero mean for the channel. And this will be my effective noise term, And if the channel G prime and the noise N prime are independent of each other, well then this will not change very much. It might even be that if this is Gaussian noise that it doesn't change anything at all. It just is another rotation in the complex domain. So after we have utilized G prime like this, we can suppose that we are forgetting about that we knew G prime. And we just look at, okay, we have a channel Y times G times X plus N. And then we are applying this capacitor lower bound without utilizing that we actually knew anything about G prime, but using this bound that was developed for the case when the receiver doesn't know anything about the channel. And that is why we call this the use and then forget technique, because the receiver knows something about the channel. It could be G prime, it could be something else, something that is utilized here to multiply, pre-process the received signal, so that we are getting something here that has a mean value that is non-zero. And after we have used that information at the receiver side, we are sort of forgetting about it. We choose to not utilize our information about G hat when we are computing the capacitor lower bound, when we are operating our decoding algorithm at the receiver side. And then we can achieve this lower bound. The second step, when we are forgetting about things that we already knew, might seem wasteful. Why should we compute capacitor lower bounds without using all the information that we're having? And in general, I would agree with that, but in multiple antenna communications, what we are dropping in terms of information might be very little, particularly when we have many antennas. Then it turns out that the variance of this term here becomes very small. So this variance term here is small, and in those cases this can work very well. And another added benefit is that we will have expectations and variance terms here that can be simple to compute. So we can compute capacitor lower bounds that have a nice expression and that we can utilize to understand the behavior of the system, and then know that we can do better than those expressions are predicting in reality by actually utilizing the estimate of the channel that we might have, for example, at the receiver side, instead of forgetting about it. If we want to utilize all the information that we have about a channel at the receiver side, then we need to compute another type of capacitor lower bound. And this is for a fast fading case with some kind of potentially partial information about the channel. So this part is the same as before. We have a transmitted signal X with some variance or power Q. We have a channel G, which is random, so it's varying. It takes new realizations for every time we're transmitting. And then what we are receiving, Y, is G times X plus N, which is some kind of noise term here. It could be uncorrelated noise. And the receiver observes Y and some kind of channel side information. You get some additional information here about the channel from the side. And omega might then be correlated with G, because then omega is telling us something about the channel. It might not be the entire channel, it might be some kind of estimate about the channel, for example. And of course, the goal of the receiver is to estimate the signal that was transmitted and make sure that we are able to transmit as much data as possible from X to X hat. And some assumption that we need to make: the signal X is independent of G and omega. So the information about the channel that is in omega or the actual channel is something that cannot go into X here. So X is selected at the transmitter side without any information about the channel. The next assumption is that we have zero mean noise. So the noise N here is conditionally zero mean when we are conditioning on the channel sign information that we're having. So N conditioned on the realization of omega have an expected value that is equal to 0. And furthermore, we have these uncorrelation conditions for the noise as well. And that is particularly important when the noise N here is containing some additional interference or something about the channel that we didn't know. And here we say now that X conjugate times N, given the side information that we have, omega, it should have an expected value at 0. So it's conditionally uncorrelated noise. And N should also be uncorrelated with G times X. So if we take the conjugate of G times X, multiply with N, then conditioned on the sign information that we're having, the expected value should be 0. So G times X and N are conditionally uncorrelated with each other. And now this conditioning becomes particularly important because it tells you potentially something about G. But even if some information about G is in omega, we still have something that is uncorrelated here. So under these technical conditions, we will now compute the lower bound on the channel capacity. We will compute this capacitor lower bound with side information at the receiver in a similar way as we did previously. And we will use the same version of the capacitor definition as before, where we have a maximization with respect to the input distribution. Then we take the differential entropy of x, and then we take the minus the conditional differential entropy of x given what we know at the receiver side, which is now both y and the side information omega. And we compute the lower bound using two steps. Same two steps as before, but now with some more complicated expressions. So the first thing is to assume that the transmitter is using a Gaussian signaling. That might not be the input distribution that is achieving the capacity. That's why we get the lower bound on the capacity. But the good thing is that the differential entropy of x can now be computed. Log 2 of pi times e times q for this particular choice of input distribution. Next, we would like to bound the second term, this conditional entropy, and we write it like this. And we are looking for an upper bound on this term, because then we have a value of it that is larger than it should be, and therefore we are subtracting a larger number, and we get something that is a further lower bound on the true capacity. So we start from the expression that we have here, then we are replacing in a similar manner as in our previous proof, y with x hat, a linear MMC estimate of x given y. And we can do that replacement because that is just like scaling y with the scalar that we called c before. And we can always undo that by dividing with c again. After having done that, we could take x hat and we can subtract it from x. And that's something that we can also do without any loss of information because we are subtracting something that we know. But then comes a step when we are throwing away information. We throw away x hat. So then we get x minus x hat. It's only given omega, but not giving x hat. And therefore we get something that is more uncertain, a larger differential entropy, because we are not knowing x hat anymore. So this term here is representing some kind of estimation error between x and x hat, given the side information omega. And for one realization of omega, we can say that, well, this might not be Gaussian distributed, but if it were, then the differential entropy can be computed as log 2 of pi times e times this term here, which is representing the variance or the mean squared error of our estimator for a given realization of omega. And then we are keeping expectation with respect to that omega randomness outside the logarithm. So that is also following the same type of steps as before, it's just that we have this additional term omega that we need to keep in mind. Next, we can utilize that we know how to compute the mean squared error of terms of this kind. We have a slightly more complicated setup now when we know omega, but it's essentially the same type of thing. So we have the expectation here, we have the logarithm, and then here we should put in the mean squared error. And previously, in our expression, we had a numerator with q, which is the transmit power, multiplied with the noise variance. And now it should be some kind of effective noise variance. And here we have also the effective noise variance in the denominator. And here we have q multiplied with the channel, with an absolute value square on. And now it should be some kind of effective channel, given what we know about the channel. This is what it will become in this case. The effective channel is the channel g. And then it's an expected value of g given what we know about the channel, the omega term. We have two things that are contributing to the effective noise. It's the uncertainty around the signal term, and it is the noise term. And under the assumptions that we were having about the uncorrelatedness of these two terms given the omega, we can write the variance as the variance of each of the different terms. So the variance of the noise given omega, and the variance of g given omega multiplied with the power of q. So this term is showing up here, and here we have the desired term. So to wrap things up, remember we have the log 2 of pi times e times q over here, and then we have an upper bound on this second term down here. This is what I have written here, the difference between them. And if we are rearranging things, we will get this expression here. So we have this term divided with this term, and the q disappears from this q, and the pi and e are also cancelling out each other. And then we have this term divided by this term, which contributes to this 1 here. So the whole expression looks like this. We have an expected value with respect to omega, the information about the channel that we're having, and we will see many different realizations of omega over time, and for each one of them we have a rate looking like this: log 2 of 1 plus something that looks like a signal to interference and noise ratio, a signal term contained in the transmit power Q, and then the absolute value square of the part of the channel that we're knowing, expected value of G given omega. And then we are dividing with our channel uncertainty, which is the signal power Q, multiplied with the variance of G given omega, plus the variance of the noise given omega as well. So this is the capacity bound with side information, the most general one that I will present in this video. And remember, we can achieve the lower bound by having a signal X that is complex Gaussian distributed with variance Q. That doesn't mean that the capacity is achieved in that particular way, but the lower bound is achieved in that way. I will now give you two examples of how we can utilize this general capacity lower bound for particular omegas. So one example is that we have perfect knowledge about the channel. If we know G, omega is equal to G. In that case, here we have the expected value of G given omega. The expected value of G when we know G is just G. So we get Q times the absolute value square of G in the numerator of the capacity lower bound. And if we know G, then the variance of G given G is 0, so this term goes away. And the variance of N given the channel G, if we assume that the channel and the noise is independent of each other, then we can replace this with the variance of the noise N, and we call it N naught, and we get this expression, which is similar to what we had in the beginning of this lecture, but we have an expected value here. And this capacity lower bound looks almost the same as in the case when we had a constant channel. The only difference is that we put an expectation here with respect to the random channel in front of the logarithm. The second example is when we have no knowledge at all at the receiver side, so omega is equal to the empty set. Then we don't have any information here, so we replace this with just the expected value of G. Here we get just the variance of G, which we can write like this. And the variance of the noise, when we don't know anything else, it's just the variance of noise. And this is the expression that we were computing earlier in this lecture as well. And since there is no randomness left inside of the logarithm here, we can just remove this expected value and write like this. And this is the expression that we were also developing earlier as well, when we were adding the expected value of G and subtracted it again to compute a capacity lower bound with no channel knowledge at the receiver side. These are two extreme cases when we either know the channel perfectly or not at all. I would say that this capacity bound with side information is particularly useful when we have partial information about the channel G and potentially about the noise N as well. Then we need to utilize this general expression. We should not forget that the proof relied on a number of technical assumptions. Certain terms should have zero mean and be uncorrelated given omega. And we need to utilize all of those properties in order to obtain this expression. So for example, if omega is containing an estimate of G, then it depends strongly on what kind of estimator that is utilized in order to figure out if those conditions are satisfied or not. So in general, we don't know. It's something that needs to be verified. In this video, we have developed a number of expressions for achievable rates, or they're also known as spectral efficiencies. These are lower bounds on the capacity, measured in bits per second or bits per symbol, and they are describing how quickly we can actually transmit data. And what is specific with these lower bounds is that they can be used to handle when we have noise which is non-Gaussian. They might be uncorrelated but not independent, and we can also deal with interference in that way. And we can handle a situation where we have partial information about the communication channels. And there are some different technical conditions that need to be satisfied for these different bounds. Some of them are for deterministic channels, some of them are for random fading channels. And in particular, this side information bound that I was presenting at the end is something that have a number of technical conditions that are not always satisfied. While for many of the other bounds, they are usually satisfied, but we need to always verify when we use the bound that the conditions are actually true.